Here we are, Tuesday, September 22nd. Your project is going to contain two parts. There's an Excel spreadsheet that we'll go to here. And what you should do is this. You should come over here to this down arrow, click on it, and download that Excel file. When you download that Excel file, it'll come up on your own computer, so it's not like you're working on the spreadsheet online. So you can do this with any of these documents, any Word document, Excel spreadsheet. All of these are mostly, sometimes they're PDFs when I create the lecture notes for the day. But if you wanted to, you could download all of these documents and print them out on your home computer. And here's just another one. Be sure that you download this spreadsheet. I'm going to take you to it so you'll see what it looks like. The other thing that you're going to want to download is the worksheet, the COVID worksheet. It's a bunch of problems that are related to the spreadsheet. Okay, I am now going to go to the spreadsheet, and that's what it looks like. Can you see it on the screen? Okay, I'm seeing a couple nods. That's good. I'm not going to really ask you to, do any sophisticated calculations because this spreadsheet will do it. And these are supposed to be protected worksheets, but one of the things I always ask you is, what is the formula? So here is a formula. And this one's related to COVID because they tell us that we should avoid large groups. And what I want you to see on this one is that even if the chance of someone getting COVID is very, very low in a particular county in the United States, even if that's the case, if you get into a crowd size that's fairly large, then the probability that someone in that crowd is infected could be a very high number. So let's just say that the population infection rate, and a lot of times they will be published at the CDC site for every country in the United States, including Bay County, Saginaw County, Midland County. All of those rates are known. So once you determine the rate, you can put it here. And by just clicking on this slider, you can increase or you can decrease the rate. If you grab the slider and slide it, you can see that it goes up like this. Now, also, when you click this, you can see that the numbers over in the formula change. But here is the formula, and it uses the complement rule here in order to do that. And there's the formula. You can also increase the crowd size. Notice that that changes the exponent here of the formula. And then it also changes the probability that someone in the group has COVID. And if they have it in COVID and there's no mitigation, nobody's wearing masks, then many people in that crowd can be infected. So there are, if you look down at the bottom, there are 4 different parts because there's 4 different components. And the COVID testing over here is one related to those tree diagrams that we've been doing. Herd immunity, or as our president would say, herd something. Herd intelligence, I forget what he called it. Number of infections is another one. So all of these involve the mathematics of COVID. I generally, with this problem, would just like you to be familiar with the mathematics. It's not about politics. It's not about what you believe. It's just the mathematics of it. If this is the case and this is the case, so for example, people from different parties might disagree on what this population infection rate is. Right now, they're estimating it, well, no, to be fairly small, like 0.007 or something like that. It's going to be a very small number. Very few people in the country are going to be infected when everything is said and done. But so we can argue about what this number is, but these formulas here, they don't really care what the politics are. You can just calculate the math to get this number over here, and this is the goal. What percentage of the, what's the likelihood that somebody at this big event that has a lot of people would be infected? So let me go to, let's see if I can find it here. I'm going to bring up this document here. So let me go through just, after I explain the spreadsheet, I want to go to a problem for each kind. And here's the one. It says, what is the probability? And you can see here that we're going to use the crowd tab for this one. There's 4 tabs at the bottom of that spreadsheet. For this first problem, we're going to use the crowd tab. And if you recall, there's the crowd tab. So we're going to be using this one. So we're going to go to, let's just do one of these, this one here. What is the probability that a person from a region has been infected with the coronavirus if the infection rate in the region is 180 per 100,000 and there are 300 people attending a wedding? So let's say you're going to a wedding, there's 300 people there, and you want to know what is the probability, oh gosh, I should probably change those. What's the probability that someone in the crowd is infected? So what we're going to do is we're going to convert that, and this is how they report them, just because when you report a percentage, it's just way too small. So let me show you what number you type in there. It says 180 per 100,000. So the rate would be 180 over 100,000. And you can calculate that with your calculator, and you get this number. So here is the rate. This is the number that you want to put into that spreadsheet. Now, as this rate, it would be 0.18%, because we moved the decimal point over. But this percentage is kind of too small. This number is too small. So the way that the CDC generally reports these infection rates are with the number per 100,000. And so they give this. But this is the number that you want to plug into that spreadsheet. Okay, so I got to undo everything that I've done. Okay, come back here and then share my screen. And okay, so this 180 per 100,000, we're going to enter in as 0.0018, and then we have 300 people. So we're going to come to the spreadsheet, and we're going to take this number down to 0.0018 right there. You can see it's 0.18%, and we're going to increase this one up to 300. And if you want to have more precision, then there you go. Now, if you set those two, notice it'll take the 0.0018 and put it into the formula. It'll take the 300 and put it in the formula, and then it'll calculate this number right here, 0.421. So you go over to the spreadsheet, and look at this. You have your first answer, 0.421. And what this means is that there's a 42.1% chance that someone at that party, at that wedding, has been infected. So if that's too high of a percentage for you, then you probably shouldn't attend the wedding. So the first 4 problems are like that. And I just wanted to go through one of them. All right, problem number 2. You're going to go to the number of infections tab. And for the first one, it says the seasonal flu has an infection fatality rate. That means everyone who gets the seasonal flu, about 0.18% of those people will die from the flu. Thousands of people die from the flu every year. We think that the coronavirus percentage is higher than the flu, just because normally when the flu is out there, We don't have as many, ventilators going and so on. There are some, but not as many. And we know that this thing is airborne. And so most of the experts that study this stuff thinks that the infection fatality rate, the IFR, is actually higher than the flu. All right, we know also that there are just under 200,000 deaths in this country. And it turns out that if you have the 200,000 number and the infection fatality rate, you can estimate the number of Americans that are infected. So let's go back to our spreadsheet and select the number of infections tab. Here it is. I think I'm going to set this up so that you can just type in the number. I think this only goes up to, let's see what it goes up to. Well, it's not even changing. But the number of deaths, if you want to put in 200,000, and then the infection, let's see, this one I think would work, 0.18%. Then the number of infections in the United States is that number right there. Again, this is the mathematics, and you have people who are vehemently argue with one another to decide what this death rate is. Some say it's just like the flu, 0.18. Some say it's much higher than that. 0.45, I think, is what they have right now. But whatever it is, the mathematics is such that if you take this number, 200,000, and you divide it by 0.18%, this is how many people. Do you believe this? Do you believe that in the United States of America, where we have 320 million Americans, that about a third of them are infected right now? That's what the math tells us. And right now they're estimating this at about 0.45. But if there are 0.45% of those who get this disease are going to die from it, then that means right now, based on 200,000 deaths, we have over 4. All right, let's go try another one of these. All right, so this one here, they talk about herd immunity, and a herd immunity assumes that a certain percentage of the population will have the infection, and if they've already had the infection and they can't be infected again because they've already had the infection, then some say that you only need 50% of the population to have experienced the COVID infection in order for the whole country to be basically immune, because there aren't enough infected people or non-infected people for the virus to live. So this one assumes that if the 50% of the population is infected by COVID and the fatality rate is 0.45%, these are actual numbers that some people believe at this point, then the question is, how many Americans would actually die? So we're going to go down to the herd immunity. The US population is, I ask you to indicate, so it's about 331 million, so I'll just get close to that. I'll say 328 million. That's the US population in this project. I ask you to look up that number. If herd immunity is 50%, then that means, I got something over here. All right, so that means that 162 million people, 50% of the population, would have to be infected. And then if that's how many people are infected, and this is the death rate, would we say it was 45? Then this is how many Americans are going to die. This is the mathematics. This number is not going to change. The population of the US is not going to change. Now, some people will say herd immunity is 50%. Some might say it's actually higher than that, 70%. And if it's higher than that, then these numbers are going to increase. And this is what they're assuming the infection rate is right now. So we could potentially, we only have 200,000 deaths right now, but we could potentially have 730,000 deaths from COVID. And this just assumes that we don't have any mitigation methods. So I think these are the two numbers, 730, 620, and that would be the answer to the first one. All right, so there's not much to do in this herd immunity one. I ask you to go and look at the spreadsheet and find the formulas. The last one is COVID testing, and I'm not going to have a whole lot of time, but just so you see, every test has a sensitivity and a specificity, and maybe we'll start off next time going through this. And we're going to assume that only 0.7% of the population is infected. So if you come over here to the COVID testing one, you change the prevalence to 0.7%, that's the prevalence. And the specificity, I forget what this number is, 89.1. And the sensitivity, much higher. The sensitivity is the probability of getting a positive reading if you do in fact have the virus. And the sensitivity or the specificity is the probability of getting a negative reading when you do a blood test if you don't have it. So I think this was 99.5. So then you're after these numbers over here to the right. I ask you in each case to identify the false positive rate and the false negative rate. And there they are. So you'll notice that when you move these sliders in every case, that the numbers in some of the formulas are changing. And so I always ask you for the formulas. So you'll have to play around with this and see what happens.